it gives response, but in order to observe its response, you will have to go to some high speed which are closer to the speed of light. So this space is no more absolute. This is responsive, but you will, in order to get that response, you will achieve high speed. You will go to that speed, then you will see the response. Like when we say length contraction means space contraction. Now that space is contracting. Our time dilation, that time is dilating, means it is responsive. So the motion here, which is based on space and time, now this, in order to keep this motion absolute, the space and time should be responsive to each other. Like you are going in a space and you are about to exceed the speed of light, then the space will extend in order to keep the speed of light the same. If light is losing the speed, the space will shrink in order to keep the speed of light the same, and vice versa with the time. So they are actually responding to each other. Let's say, for example, this board, this is not responsive, right? If you do this to a human, they will respond. But we say that it is not responding. Now, it will respond if you knock it the frequency at which it can give you response. Like you just start hitting it with the resonant frequency. What will happen? This will scatter into pieces. It will respond, but you will have to reach that limit in order to respond. Space is absolute and time is absolute when you are at a low speed, like in classical mechanics. But when you are at very high speed, then space and time are responsive to each other. And that was, you can say, the relativity or the relativistic mechanics, the special theory of relativity, a different regime that worked. And then when you consider the Maxwell equations, inside the Maxwell equation, let me focus on these two and let me write them in a very simple form. Here, what the Faraday's law is telling you, this is a space derivative, right? A curl or a space derivative. So I can write this one is dE over dx is equal to dB over dt. Variation in one in time is the variation in the other in space. Look here, this one, the Ampere's law or the Maxwell corrected Ampere's law. Forget about this term, the constant term here. This is dB over dx is equal to dE over dt. Einstein obtained his PhD degree on these equations. Maxwell did them. They were not the Maxwell equation, but he just formulated them, corrected them, and he got a Nobel Prize. Einstein completed his PhD on this. The article he published on the moving of electrodynamic objects in 1905 was actually this thing. Now, how he is perceiving this thing, that B and E are not different things, but they are just the space and time variations. These are considered as different fields, although Maxwell said that this is not another field, but it is just charge and motion, are electric field and varying electric field. There is no concept of magnetic field. But he said that this is just a game of reference. Like, let me consider that, let's say I'm a charged particle and Musa is also a charged particle, and I'm at my place and he is at his place. So what is the force of interaction between him and me. This is electrostatic force, right? We are having electrostatic interaction. And now when I start moving, due to my motion, now I am called current. And he will feel that electrostatic portion but not the effect of my motion. But if he started as well, he did a little bit movement, then he will feel my magnetic field. He will become a magnetic field. He will become a current. I'll be a current. And he will be just considering me as magnetic field, not as electric field. So it means this is all the game of the reference frame. When every was in motion, every frame is in motion, then the electric field and magnetic field has no difference. To you it will be electric field, to me it will be magnetic field. Or let's say, now I'm moving in a car, and I'm a charged particle and I'm moving in a car. Now to myself or any other charge inside my car, this is electric field. But to the outside observer, I am magnetic field. So he said that this is just the game of reference frames. They are not different fields. It's just the game of reference frame. In one frame, you will see it as a magnetic field. In another frame, it will be electric field. So as long as they are inertial frames, means A equal to 0 frames. Inertial frame you call non-accelerated frames, either at rest or moving with a constant speed, but rest we exclude. So it means they are moving with a constant velocity. Now when A is equal to 0, this situation, inertial frame of reference, and the fields will actually switch in and switch over with one another. They are like that. When you consider space and time, then how you define space? Or let's say we start from mass. How we define mass? The quantity of matter in a body is called mass. Then you should know matter. What is matter? What is matter? Yes, that occupies space. So it means we should know space then in order to know matter and then to know mass. So what is space then? Space is the distance which a body travels in a given duration of time. Then what is time then? Because this is something like I ask you, how old are you? And you say, I am 2 years older than this one. Then I cannot know your age unless I know the age of him. And he say, I am just 3 years younger than this one. And it goes on. And finally she says that I am this much years. So then I will come to know all the age of you. So you said mass in terms of matter, matters in terms of space, space in terms of time, and then what is time? We again say time is the interval or the duration in which a body moves from one point to another point in space. So again we come to space. We define space in terms of time and then time in terms of space. So it means they are not separate from each other. They are coupled together. So you cannot you cannot separate them out. And which is the thing which is coupling them? It is motion. Right? Motion is coupling them. And when this motion is very high, close to the speed of light, then both of these two respond differently. They shrink or they stretch. Okay, so it is to them that they behave differently. When all this thing was done, Then it was applied to some problems. It explained the situation. This thing explained the situation of c, the speed of light is absolute constant. This explained the lifetime of the elementary particles. When this theory was applied to some cases, then it was not giving the right result. And about some of the paradoxes, like the twin paradox. If you are interested in the special theory of relativity, then we have already recorded and uploaded lectures on the special theory of relativity. They are available on the internet, on the channel. So over there we have explained them, like the twin paradox, like the bar and ladder paradox. So those paradoxes, some causality, you have studied special theory of relativity. In your intermediate level, you would have studied like causality, the cause and effect, and which can be alien, and all these things, simultaneity and other things. But let me discuss this one only according to our topic. If you are interested, you can watch those videos yourself. Twin paradox. Now you know about the twin paradox, that twins were there on the earth and one remained here and the other goes in a space shuttle somewhere. It says it's a shuttle and the other goes in this one. When he returns back, let's say they were both 10 years old when he was departing, and let's say after 10 years when he came in, this brother was celebrating his 20th birthday while this was celebrating, let's say, 17th or 18th birthday. So he became 3 years younger than him. Then it's a paradox. The theory is not explaining this thing. It cannot explain this thing. In reality, this wasn't a paradox at all. It was the wrong application of the theory. The theory was for the non-inertial frames. And look, whether this situation is inertial frame that we are applying. When the shuttle is starting from here, it is non-accelerated because it will accelerate to reach that speed. When he will be returning back, it's a curved motion. Curved motion means that it is in accelerated motion. So there is acceleration. When he will be getting down from it, again it is in accelerated motion. So if in the meanwhile this was non-accelerated motion, but at all other stages it is in accelerated motion, so it means it is a non-inertial frame of reference on which we are applying a theory of inertial frame. So it is the wrong application of the theory. And that's why it causes a problem. It causes a paradox, right? So means its application wasn't right. This was not a paradox at all. Further details you can watch there. And Einstein then took 10 more years in order to include the acceleration non-equal to zero situation. After 7-8 years, he presented another theory, which is the general theory of relativity, in which A is non-zero for the non-inertial frames. But some objection came on that one, and then he took 3 more years, and in 1915 he just presented that theory, the general theory of relativity. And now 100 years has passed on this theory, and so many people received Nobel Prize in the explanation of this theory. Now this level of mathematics was very high. Like it was Einstein who was asking the mathematician that this is the situation, no, develop mathematics for this one. It's a very high level mathematics, and we will be covering this mathematics in our PhD level course, Electrodynamics and General Theory of Relativity. We will be covering it. So if you want, you can follow with us that course. So when it's a very high level mathematics and the mathematician just write equations for you, then there should be someone who can decide whether the equations are right or not, whether they are telling us that thing or not. So it was again Einstein who will be deciding whether this thing is right or this is not right, or if this is to be modified, how it is to be modified. So it was again Einstein. That's why it took around 10 years. Like Maxwell equation, the very established theory, 150 years has passed. 100 years has passed, very established theory. Some of the proofs of this one, we just took 100 years in getting the evidence of gravitational waves, which was predicted by this theory. But after 100 years, we were able to measure those gravitational waves. Is we know that there is no inertial frame of reference. Do you know any inertial frame of reference? All the frames that we are having, they are all non-inertial frames of reference. And that was the reason that we need a theory for the non-inertial frames of reference. Sometime in science we do have things which don't exist at all, but we have science for that one because they are the simplest. Like we say not equal to zero. But what is this situation? Do we have any situation in which a is equal to 0? In some limits, yes, but not. Can we have 0? 0 is not scientifically available to us. Is there anything which is 0? Yes. We use 0 a lot in our science, but it is scientifically not available. Any example of 0? Like we know that this globe is 13-degree inclined from north to south. That's why rivers are flowing from north to south. Now this is not 13.000 or infinite zeros here. When we say the electron mass, then the electron mass is not 0. This is 0.000 and so on. So we have no availability of 0. Just like how you define vacuum. Vacuum, you define vacuum, the state of matter where there is no matter. It's vacuum. 0 is called the vacuum of mathematics. That it is something, though it is nothing. Right? It is something. Because if you multiply it with something, it will become 0. You divide it, you don't know the result. You write 1 0, situation is different. 2 zeros, it's different. You write on one side zeros, it does matter. On the other side, it doesn't matter. So 0 is very complex. Here, so the mathematics was so advanced, that's why it took 10 years in order to include the concept of non-inertial frames. A not equal to 0, you write is G. G is not equal to 0. You remember that Newtonian mechanics or the universal law of gravitation, two masses are attracting each other. So Newton said that it is attractive force between the masses, the gravity. But Einstein said that no, gravity has nothing to do with the mass. This is just, you can say, the space-time curvature. This is actually this is a fabric, space-time fabric. It is completely flat, so it is inertial frame of reference. Speed of light is constant here. But when you put another an object here, it will produce some dip in this one, some curvature in this one, and it is purely a geometrical property, this gravity, but not a property of the mass. It has nothing to do anything with the gravity. Yet we don't know exactly that what is gravity. We are yet in search of this one, but some clues they were explained by Einstein, and all these things then combine when the particle size is very small, when this m that we discussed there is very small, when the v is very high, and when the field concept is there, when it is not electric field or it is not a magnetic field, it is just a field and it is of the quantum nature as well, then we enter another subject which is quantum field theory. So quantum field theory is explaining then these things, and the Maxwell equations which we study here is 4 equations, they convert into one equation, right? Relativistic quantum mechanics, quantum field theory, those equation becomes one equation, and we enter into more and more dimensions, like when we will be going from special theory of relativity towards the general theory of relativity, we introduce the 4 dimensions, and in those dimensions we come to know about the rest mass energy. They becomes evident in more dimensions. In quantum field theory we move to 5, 6 and more dimensions, up to 11 dimensions. For example, we study the string theory, 11 dimensions, or we call it a theory of everything. So all they couple with each other. When we will discuss in the next lecture the forces, then we will explain this thing in terms of forces, the natural forces that are here with us. Okay, thank you.